So let's start chapter 2.3 by explaining exactly what a linear system of equations is and how it can be reinterpreted as a matrix vector multiplication. Let's go to it. So a linear system of equations is basically a collection of different equations in which we have certain variables which are unknown quantities. Okay, so let's say that you have a certain number of unknown quantities. So we could call them whatever we want, but for simplicity, let's call them x1, x2, and let's say we have n unknown quantities. Okay, so we don't know the value of these numbers. These are our unknowns. But we know that these variables or these quantities fulfill some set of equations. Okay, so this is a system of equations because they are equations that all of them must be fulfilled simultaneously, all at the same time. So this would be a system of equations in general. But here we are going to be interested in a linear system of equations. What's the difference? So linear system of equations means that the unknowns, x1, x2, and so on, they only appear multiplied by a scalar, and that's it. Yeah, so you cannot see x1 squared or square root of x, or you cannot see the cosine of x1 or exponential of x1. So all those operations are not linear operations. The only thing that you see in this collection of equations is some number times x1 plus some number times x2 and so on. Okay, therefore you can write them in the most general case. You can write them like this. So you have your variables, which are the unknowns, and each of the variables is multiplied by a certain scalar, which is just a number, okay, a real number or maybe a complex number. So each of the variables is multiplied by a certain coefficient, and these coefficients are called the coefficients. Now these equations might involve then a coefficient which doesn't multiply any of the variables. So it's a coefficient that goes alone. So this would be the b coefficient here, which we can always move to the other side of the equal sign. Okay, so we always collect all of the coefficients which multiply variables on one side, and then the coefficients that do not multiply any of the variables, we put it at the other side. And these are called the independent coefficients. Okay, so this is the most general way in which you can write a linear system of equations. Let's see, for example, a linear system of equations could be x plus y equals 2 and 2x equals 2. That would be a linear system of equations, yeah? So how could you write it in the form above? Well, you could say that 1 times x plus 1 times y equals 2, and 2 times x plus 0 times y equals 2. So you just have to write zeros. If a certain variable does not appear on some equation, you just use a 0 there. Yeah. So this then would be the coefficients 1, 1, 2, 0. Then the independent coefficients 2 and 2, and the variables would be x and y. Okay. Now, how do you usually solve in the past these equations? So in the past, what you did was normally you just labeled each equation, yeah? So you said this is equation number 1, and this is equation number 2. And then you add them together in certain combinations, or you substitute one into the other, and so on. But it was like a trial and error method, yeah? There was no real exact science to it. However, in this chapter, we will see an algorithm to always solve any linear system of equations, and we can never go wrong. And it's the way that computers, for example, will do it. Okay. So why is this linear system of equations chapter included in the matrices section? The reason is that this linear system of equations, which apparently has nothing to do with vectors or with matrices, it can actually be written simply as a matrix A times a vector x equals a vector b. How can we do this? Well, matrix A is written here, basically has all of the coefficients arranged in rows and columns. So each of the rows corresponds to a different equation. So the first row would have the coefficients of the first equation. Yeah, and then each of the columns correspond to the coefficients. The first column would be the coefficients for x1, the second column would be the coefficients for x2, and so on. Yeah. Then your vector x is just a vector which contains your n variables or unknown numbers. Yeah? So you just put them in a vector. And then vector b is just a vector which contains the m independent coefficients written as a vector. Yeah. So if you actually do the matrix vector multiplication here on the left hand side, you end up with a vector in which each of the elements corresponds to the left hand side of this system of equations, basically a linear combination of all the variables. And then you equate that to b1, b2, b3 up to bm, and that gives you the total system of equations. So this means that indeed this linear system of equations may be written as a matrix vector multiplication. But this is amazing because it means that something that didn't look at all related to matrices or vectors, suddenly we can reinterpret it as ax equals b. So we have a vector x, which is unknown, so we don't know what this vector is. Yeah. So maybe we have three variables, x, y, and z, or let's call them x1, x2, and x3. And we have some vector, and we don't know what this vector is. And this is vector x. And we don't know what this vector is. But what we do know is that when we apply a linear transformation, and we know that linear transformation because we know the coefficients from our equation. So we know what this matrix A is. So we apply some linear transformation to x, and we end up with a vector b, and we know that vector b. So we know what that vector b is. Yeah. So somehow we just need to find what vector x was. And this way of putting the problem, which is very geometrical based on vectors, is a way of actually solving any linear system of equations. Of course, here, the case I showed you here, where I used three variables, I also assumed that matrix A is a 3 by 3 matrix, converting 3D vectors into 3D vectors. So I was doing a system that looks like something like this. Something like this. This is a system of three variables and three equations. Yeah, three unknowns and three equations. That's why we can picture it as three-dimensional vectors being converted into other three-dimensional vectors. Because the number of equations is 3, and the number of equations will be the dimension of vector b. That will be the number of equations that we have. Yeah, and then the number of variables in this example is 3, and that's why vector x can be also pictured as a three-dimensional vector. So in this case of three unknowns with three equations, we can picture vector x and vector b as three-dimensional vectors. But in general, they don't have to be three-dimensional vectors. Maybe x is a 10-dimensional vector and b is a 5-dimensional vector. Yeah, but we know that there is a matrix A that relates them. So now the problem of solving this system, this linear system of equations, is reduced to the problem of finding this vector x, which gets mapped to b after doing a linear transformation. And therefore we can use all of the theory that we have learned about linear transformations, like the null space, the range of a matrix, and so on, to solve this linear system of equations. So next we will look at the method called Gaussian elimination to solve this system. Thanks for watching.